as they are exploding, there must be a difference between if the core collapses and then stops at a neutron star, so it just collapses and goes, but there's a point beyond which it can't go, versus it just goes and collapses entirely. That is what people are now looking for. That when a star explodes, and we look at stars, there's about, fairly good programs to find stars that are exploding. Not so much in our galaxy, but nearby galaxies and so on. So people, and they're looking for the signature that they expect that either leaves a black hole or a neutron star. So that's what they're looking for right now. And I think they found it. I haven't been following it very closely, but there's good evidence that you can tell the difference between when a star exploded and left a black hole and a star exploded and left a neutron star, without having to wait for billions of years or for you to go there or have some binary.
Yes.
Oh.
Yes.
Could you comment a little bit on Hawking's theory that eventually a black hole will become a white hole if given enough time? I don't know, maybe 50 billion years or something. So what's involved with that time span in terms of the physics that are causing the black hole to degenerate into a white hole? And is that a controversial theory at this point, or is it accepted?
No. In fact, it was all a part of what we were talking about, the Hawking radiation. The idea was that for this to really work, you need a very small black hole. And there's no way to generate a small black hole today. And we're talking about an Earth mass black hole, not an Earth-sized black hole.
Mm-hmm.
An Earth mass black hole, which would be very small, I don't know, a few centimeters across, but it would be about an Earth mass, I think, or maybe even smaller. I don't remember the details on that. But the idea was that if you generated a black hole like that, and because of the uncertainty principle, if it was emitting particles and radiation, basically particles out of it, it's a non-linear process. It starts off very slowly, but then as it gets towards the end, it suddenly becomes extreme. So suddenly lots of particles are leaving, so it looks like basically it's exploding. And in fact, it is. All this material is coming up in a very short period of time. And the problem was that nobody could make a black hole like that. But they said in the beginning of the universe, the conditions were sufficiently different that you could have possibly made these mini black holes, and that's what they're generally referred to as the mini black holes. So the mini black holes would take anywhere from 10 to 50 billion years until they went into this what's called evaporation process.
Right.
And that last bit of evaporation is actually very explosive. And so people started looking for it because, hey, it's been around 13 billion years since the beginning of the universe. So if we made these mini black holes at the beginning, so now we should be seeing them exploding. And so that was the idea. No one has ever come up with a definitive explosion in the universe that says, oh, that's an explosion we don't recognize. It looks more like Hawking's mini black hole exploding. And that's the general idea. Same idea that things will, these mini black holes will eventually emit and go away.
My question is more on the trivial side rather than the science side. Number one, could you briefly describe what happened with the Big Bang theory, Partsunian's position, and so forth? What does today's textbook say about it? That's number one. Number two, how many Armenian names are recognized the way you just described? For example, was it Markarian galaxies? If there are that kind of stuff. And number three, who are your Armenian peers today all over the outside Armenia who may be involved in the field?
Okay, first, so there, the Big Bang Theory, the reason it's called the Big Bang Theory is the name was by people who didn't like the Big Bang Theory. They said, oh, that's like, that's like a Big Bang you're talking about. But it stuck. It was a great controversy in the 50s and 60s when it initially was proposed. But the evidence started mounting for it over the years. Unfortunately, Ambartsumyan never really got on board with it. He disputed it, and that really, I think, combined with the fact that Soviet systems are very top-down, started marginalizing, I think, what the Armenians could contribute, because they all stuck with Ambartsumyan saying, oh, we don't think the Big Bang is the way you described it. The beginning of the universe is not what you described it as. The competing theory was something called the steady state theory, so he was much more of the proponent of the steady state theory, that the universe is infinitely old. Things change within it, but there's no one singular beginning of time, which was a fair proposal at the time, but the evidence just didn't bear it out, that the expansion of the universe, although you can account for it in the steady state theory, is is an observable. You just look at there, things are moving away from each other. And the critical difference came in on the radio astronomy side, which is what's called the cosmic microwave background. All you need to know about that is that if you have, everybody knows that if you expand a gas, it cools, and if you compress a gas, it warms up. That's the way it works. That's why when you've got your little spray can and you're spraying and spraying and spraying, suddenly it feels cold. Why? The gas is expanding, it's taking temperature away, so it feels cold. But if you compress the gas, it'll warm up. If the universe, you're compressing it, most of it is a gas. In the past, it has to be warm in the past. So the remnant temperature has to be there. And the cosmic microwave background is in fact exactly that. It's this remnant temperature of a hotter time. So this was a really key piece of evidence that converted a lot of people. Apparently not Hamartsumia, and there are others, not just in Armenia, other places who were just not very convinced of this idea. But because he and many others in his group did not follow this, and I think they just, people paid attention to them on the things that they agreed with, but they were no longer in the mainstream, which was unfortunate. One of the things that we have here, and this is a personal opinion, is that we don't have as strong a top-down system. And I think that's one of the problems with the top-down system. If the guy on the top is right, great. If the guy on the top is wrong, can you argue with him? He controls your money, he controls your funding. So that's a very difficult position to be in. I'm not saying that everybody just followed him just for the money. I'm just saying it creates a very difficult position within a scientific context. You want new ideas to come in, even if they're wrong. But I think it's a critical thing to have that sort of more free exchange of ideas, and that seemed to be a little bit limited. The reason I actually also put up the museum sign, it's one thing to respect Hamartsumia, and he so certainly deserves it. This is not anything against him. I mean, Chandrasekhar wrote an amazing obituary for him because he thought he was such a great astronomer. The contributions that he made in all the other areas that were not Big Bang were amazing. But it's become a little bit too reverential. You should never revere anybody in terms of science and so on. That is, it's great if they're right, but you should always consider the fact that they might be wrong. Even Einstein, whenever they would, challenge him, Einstein thought quantum mechanics was wrong, and he in fact became more marginalized because he never followed quantum mechanics, but that was where physics was going.
God doesn't play dice. God doesn't roll dice.
Yeah, Albert Einstein said God doesn't roll dice with the universe, that statistical things should not be part of physics. Of course, his friend asked him, Albert, how do you know what God thinks? So that's the thing, is that has been an unfortunate aspect. So that's, he basically put Hamartsumia and others more out of the mainstream, particularly those that followed him. And it was not a good position to be in, particularly, for how small Biragon was. It was, I mean, but going to your second question though, in terms of Markarian is definitely the best known. He died unfortunately too soon, but he was the best known, and the contribution that he made, that catalog is an incredibly valuable catalog. It's been surpassed by others, but still the objects that were in his catalog are still referred to by their Markarian numbers. I mean, when people go and talk at conferences in AGN, they talk about Markarian 6 and Markarian 3 and Markarian 48 and so on. Those are part of the lexicon of astronomy. There's nobody else that has gone to that level, I think, within the community. There was another survey done that was by Arkelian. They're known as Arkelian galaxies, not as well known. But Biragon also made an effort to not distance himself. They did a second survey, and Markarian didn't do it, so they couldn't call it the second Markarian survey. But then they wanted people to know that it was the same type of survey. So in fact, they renamed the Markarian survey the first Biragon survey, and the second one as the second Biragon survey. And in fact, there's several objects that people follow by their SBS name, second Biragon survey name. So in that sense, Biragon is known. So if you're studying an SBS object, it's the second Biragon survey object. So that's in that sense. As far as my peers, there are several Armenian astronomers, certainly that I know in the US, not a very terribly large number, but certainly the most famous one is Yerban Terzian, who was the head of the Department of Astronomy at Cornell for many years. He's still there. I think he just stepped away from being department chair, more because I think he had a heart attack. So, but he's well now. He's doing okay. And I have and whenever we go to the American Astronomical society conferences. I've tried to actually get in touch